Quickly, because probably you all want some cake already. So yeah, you can read the title for our project. What it doesn't tell you is the specific field in which we focused, which is flooding events. And we already got introduced, and you can read our mentors. So a short overview, what our projected workflow was about. I will quickly introduce the motivation and goal we had, principal model design, and then a few things to data, feature selection, the machine learning model setup, results and outlook, so usual structure. And there are 4 important parts in the whole project. The first was getting all the necessary data from ECMWF and ECMWF and Copernicus. Then you have the training period where you tune the models, the application to some new data which the model hasn't seen before, and finish with concluding remarks. So what was the motivation? First of all, we tried to model river discharge, and it's a highly dimensional problem. Many meteorological and hydrological parameters go into it and have complex interactions. So usually you have coupled dynamical models where some meteorological input goes into a kind of a rainfall runoff model, and you have complex interactions with the surface itself. And the question we asked ourselves is, can we find some statistical connections based on the machine learning techniques with where comparable skill can be established when forecasting them? And so the goal is, first of all, it's a very explorative experimental study. So we do not have some very specific set out goals. Our goal was to try a bunch of different machine learning techniques and see where they are different, what is the gain, and we benefit from them. And the second goal, or an accompanying goal, is to make everything open source and reproducible. And we therefore heavily used Jupyter notebooks. We have also code which we run in just Python files and scripts, but we prepared a minimum example, so to say, which you can run just by using the notebooks, where all the functions and everything used is contained in. So a few words to the principal model design. The guideline which we had in mind was you determine some point of interest. In this case, for the case which you see afterwards, we used a basin in the upper Danube catchment, and the point here is Passau, which will be our reference point for the results you will see. And the first point is you need to find the upstream area which is affecting the point. Usually, if you just use the outflow point from a catchment, you can use the catchment via some kind of shapefile, and then you already have the corresponding area which is necessary. Second, we have a lot of our dimension is very high in terms of features which can go into the model, and that's why we use spatial averages of the catchment as predictors. And our predictant, as already said, is the discharge at this specific point. And the data mostly consisted of all the feature data was from the Error 5 reanalysis, where we had precipitation, runoff, snow depth, and a few other parameters, and river discharge from the Glofas reanalysis as our predictant. So the data download, we download all the data, all the Error 5 reanalysis data with the Climate Data Store API. We also wrap the standard function in some multiprocessing tools so that we can start parallel requests for the monthly data, just to speed up the whole download process. And for the predictant from this discharge from the Glofas team, we received them directly from the Glofas team via an FTP server. And besides the reanalysis, which we used as predictant, we also have 4 forecast reruns for a specific event, which we will look into in detail. And for the pre-processing, we heavily use the CDO, Climate Data Operator, for the reason that it is the standard used to pre-process netcdf files on our university server, and we were allowed to calculate there and do all the stuff there, so that's why we used it. And yeah, for pre-processing the hourly error 5 data. And what we needed was to generate the daily averages, to generate daily accumulated precipitation for the precipitation variables, to extract the data from the bounding box, to concentrate it to the spatial region, because the data in itself is of course globally, or it can be further split down, and merge everything into one netcdf file, because the data itself is on a monthly basis, and of course it's easier to just generate a small, for example, a small sample netcdf file which you can upload on GitHub, and it's obviously more easy if it's only one file.
Right. So now that all features are ready to be used, we can use correlation analysis to see if we can drop some of them, some of the input features, to reduce our input dimensionality and improve the generalization performance of the model. And some variables that we used were, for example, a runoff or precipitation, not only large-scale precipitation, but also convective precipitation, the soil moisture content, and snow depth, and the daily change in snow depth as feature. But not only the variables itself, but also time-shifted ones. That means that we also take into account the precipitation of yesterday, of 2 days ago, and up to 4 days ago. And before that, we accumulated the precipitation. So we used the precipitation of day 5 before now, and to day 11 before now as input feature. And then going into the past, we more and more increased the time period that we are aggregating over, and put everything into the correlation analysis. And what we then saw was, how do we change to the next? The result of the correlation analysis was then that the most important from a linear correlation point of view was precipitation, convective as well as large-scale precipitation, the time-lagged ones, and runoff, no. But what was also seen is that the total column water vapor, the time series of that tracked especially the precipitation time series. So due to this collinearity, we dropped the total column water vapor instead for having the precipitation. And time-lagged runoff was correlated to the runoff itself, so we dropped that as well. Now, as we selected the models, we need to somehow select or bring down the dimensionality of the model, because we have the data, of course, as a grid point data, and so we just need to somehow aggregate this spatially. At first, we tried a simple approach of clustering it spatially, but this didn't show any improvements, so we just used the catchment averages. And of course, to allow the model to capture these memory effects in discharge, so to have this decaying discharge at some point, we added time, as I just explained before, that are increasingly aggregated. This can be seen from the lower right-hand picture, in which you can see the daily precipitation in blue, which has, of course, large variability over time. And then, for example, shifted one that is also aggregated over a few days, from 5 to 11 days before now. And another one that is aggregated 12 to 25 days ago. So at some point, it tells you this was the precipitation amount of the days 12 to 25 before now. And this, we kept increasing the time span of that until 180 days, so we have enough input information in our model. So which models did we use? We started out with a linear regression model to have a baseline to compare with. Then we tried the SupportVector machine that is allowing some smaller errors in the discharge prediction, so that we are not really interested in the kind of really small changes in discharge, but really impactful changes in discharge that are the ones that we are interested in. So this is the motivation for SupportVector regression. For gradient boosting models, these are also very powerful, and they've proven to be fruitful in other applications, and they are iteratively building trees and improving on the tree that was built before, so the error is iteratively going down. And as a last model, we introduced a neural net that is using, like the other models, time delayed features, and so we called it time delay neural net. But it's just using the same features as the other ones to use. For training, we used the 25 years starting in 81, and the validation period and test period had also to incorporate many years to have large impactful events within them to really evaluate the models. So another thing that is probably not so common in hydrology models is that we have not predicted the absolute value of discharge, but the daily change in discharge. So this comes from the motivation of predicting, like in weather forecasting, you ask yourself the question, I have this measurement of discharge today, and how is it going to be changing in the next 14 days? So we're just predicting the differences, like you can see in the red arrows going up and down. And then, before evaluating, we do the cumulative sum of it and add the initial value of the discharge. So we arrive at our prediction, day 3. And another reason is that the distribution of your predictant is more Gaussian-like, and like you see in the right-hand side picture, the distribution of discharges as it is in absolute values. There's a high important right tail of the importance of the impactful cases. Now we are zero-centered, and we hope that improves the training time and the convergence of our models.
So let's look at the model specifically. So first of all, the linear regression model, which is kind of our baseline forecast. You can see here. Let's start with the plot. You can basically see here. Let's start with the start. You always have the initial time step, then you have a 14-day forecast, and then we started on the next day with the next 14-day forecast. And you can clearly see that, for example, when you look at this peak, the green line there, maybe you can see that the development of the change in discharge was captured quite nicely. But you can also see, like for example here, where the model predicts this very, very strong downfall, which was not observed at all. So this is definitely not perfect. And starting, you have for a standard ordinary least squares linear regression, you do not have any hyperparameters to optimize. So basically you just load it in, you put the data in, and you get the result. The Nash subcliffe efficiency was 0.84 for this forecast. For the next model, the SupportVector Regressor, our strategy for the hyperparameter optimization was basically that we use a standard grid search where we have different hyperparameters, we have different settings for all the hyperparameters, and we just run every setting. We just try every setting and then look at what is the best setting. And you can read the best setting here, the polynomial kernel, C100, blah, blah, blah. And you have a Nash subcliffe efficiency of 0.68. And if we quickly look at the time series, you can see that, for example, in the first steep increase in discharge there, that this is captured quite nicely by the model, and in another case here as well, in the middle of 2010. But yeah, of course, you still have some very strange developments, or not strange, but some developments that weren't happening at all. For the gradient boosting regressor, the strategy was basically the same. You have a few hyperparameters which you need to optimize. Yeah, and by the way, I didn't say it in the beginning, but obviously you use the training period to train the model. You use the independent validation period where you predict the discharge, and the testing period is just for the results after the whole optimization where we use the best model. And yeah, for the gradient boosting regressor, we get an even better Nash subcliffe efficiency of 0.89. And something you do have to keep in mind, because these are quite high scores, you have to keep in mind that the scores are calculated with the absolute values, and that's why they are in principle from the baseline very high values. But you will see afterwards when we show the results for the test period that we compare against the persistence. So you have to interpret the scores not as absolute 0.85 or whatever value, but as how much improves the model, the forecast over the persistence. And yeah, here basically the same. It looks a little bit better than the models before, but I won't go into detail.
And for the time delay neural net, the procedure is quite the same. We have a few hyperparameters, we test them, run them all, and compare the metrics on the validation period. And it seemed to work out best with one hidden layer, 64 nodes, and 1,281 free parameters. But this is not really free parameters, because we used the dropout layer with 25% of dropout. That means with a probability of 25%, we leave the node out and do not use it for prediction. So the model is not able to, or may not, use one specific feature to predict the event in all cases. It needs to focus on all of the input features, and it cannot only give a large weight to one input factor. The model structure is that easy that we can visualize it here. So we have input variables like x, 1, 2, 3, only that the list has to be continued to 16. And then we have these linear equations that are input to the 10H, and the output is then fed into a batch normalization that improves the model's convergence time, and a dropout layer that regularizes the model so that it may not be too sensitive about one feature. And the RMSE is the best of the discussed models. So we can now look at the results of the whole test period. The whole test period incorporates not only the extreme values, the most impactful changes in discharge, but also times where you have low flows and times where there is not so much change in discharge, so the Nash-Sutcliffe cliff efficiency values are quite high. And yeah, as Sebastian already said, you have to look at the improvements compared to persistence. The best model seemed to be, in this case, the time delay neural net followed by support vector regression from 10 to 14 days out. In the beginning, there is not so much difference between persistence and the machine learning model. But if we look closer into the testing time period, we can select 4 time periods that were more impactful, and we can now look more closely into that. And one is the most dramatic case because it really caused flooding in the Upper Danube Basin, and this was the 2013 case. The upper left picture tells you now the results for the first sample period, and as you can see, the amplitude is not covered by any of the models, and they are using their reanalysis values, so they should be able to capture it, but they did not. But at least 2 of them, the time delay neural net and the gradient boosting, were able to capture the shape of the increase. And if we take all 4 periods together, so we leave out the time spans where there were only slight changes in discharge, and we only look at the impactful time periods, then we see much slower Nash-Sutcliffe efficiency values because it is more difficult to predict the discharge then. And even in this case, the neural net was able to achieve quite good values in terms of Nash-Sutcliffe efficiency, while the other models dropped significantly in their metric.
Yeah, and if we now look at the special case, the 2013 European flood or flooding event in the Danube Basin, especially in the Danube Basin, we can see the reanalysis here, and we now just add another layer of models, so the regression. Although you can see that kind of the shape and the peak, that the direction, even the second one, is captured slightly by the model. The amplitude is obviously far off, as you can see. Now we add the SupportVector Regressor forecast, and you can see that it captures the development pretty good. Third, we have the GradientBoostingRegressor, which is again similar but a little bit better than the linear regression model. In terms of the amplitude, pretty same, but the shape is captured more nicely. And for the final step, we have the neural net, which is in the performance is similar to the one of the SupportVector Regressor, qualitatively speaking. And what you see, the gray lines here are the Glover's forecast reruns, which started at 4 different initial times before the flooding event happens, and no ensemble member didn't really capture the value of the Glover's reanalysis. Although we talked to the EFAS team before, during the lunch break, and this issue, they know that there is some issue, and that because inherently because of the setting, how the reanalysis and how the forecast reruns work, there you can expect that it doesn't always capture everything in the reanalysis to the point, so to say. And also you have to be mindful that the first initial time from the forecast rerun is the 18th, so you have almost a 14-day lead time for one of the ensemble run, and the last one is at the 29th. So you are looking here at like kind of the 5, 6, 7 day forecast time, and yeah. So for this specific example, we do not have the metrics shown here, because this is really just this one example, and of course the metrics are highly skewed if you just compare 2 points with each other. But this tells us this was should add that this case from the 2013 flooding was the highest ascent in all of the data from 1981. And yeah, the neural net and the SupportVector Regressor captured it quite well, but the gradient boosting and the linear regression model did not. Even though the gradient boosting regressor had kind of a similar performance, especially to the SupportVector Regressor in terms of the overall discharge value, but when it comes to this single case, yeah, it doesn't capture the development at all. So we jump to our conclusions. So, as already said, the neural net and the SupportVector Regressor were able to predict this extreme flooding event despite a relative simple setting. So we didn't modify the models, we simply used them how they are brought to you by scikit-learn. Of course, you don't even have you cannot really modify them in a hefty way. Yeah, and what we concluded is that they may provide cheap additional information to assist in forecast. So a forecast to run one setting over the training period there, it just takes a couple of seconds on the university server, which had 16 cores. So it shouldn't take maybe up to a couple of minutes to run it on a standard laptop, and you may just get an additional information which could provide some of you. The linear regression and the gradient boosting regressor were not able to predict the increase in this case, although I already said that. And looking into the future, additional tuning of the model is of course interesting. We already heard from the drought team before that they used entity-aware LSTM, which is newly published and which is quite a good idea to implement some sort of model, some sort of architecture like this. And this is where the strength, in our opinion, of neural nets come into play, because you have basically the entity-aware neural LSTM consists basically of 7 equations, and you can just modify them as you want, and then you get the whole new architecture, and you can adapt it very specifically to the problem you face or the problem you want to model. And this is a strength that only the neural nets exhibit.
Yes, and as our previous team already said, with the newest developments in the LSTM models, you can put in an information that is stationary, is not changing in time, but is, for example, grid point dependent. And you can also incorporate spatial dependencies, spatial features, like it varies, the discharge varies depending on where the precipitation happens. But in current models, they do not exploit this, they do not use the spatial information. But with convolutional neural nets, you could of course quite easily do that. We tried it with convolutional over time, but the network did not converge. But I mean, we have enough experts here, and probably we get it to work sometime. And then we could also use that model not only to predict one catchment, but also to predict multiple catchments and to predict all points in the river network, probably. And that's what the second point is about, a more comprehensive case study for different kinds of catchments.
Yeah, we came up with a concept idea of a coupled model where you put together 2 different models, but I think due to brevity's sake, we will skip over that, and if anyone is interested, we can talk at the cake station about it. But just to mention a few words, it's basically you have the river network, and we call it the transport model, and the transport model just predicts the change in discharge based on all the upstream grid points. And then we have a second model called the local model, which is calculated for every points in the grid network and predicts the local change in river discharge based on all the precipitation and other meteorological and hydrological features. And this together produces then the forecast. And I just quickly want to point out, you may have noticed in the lower left that we had all the GitHub links, and at the slides before we always put the link to the corresponding notebook there, so you can probably get the presentation via an electronic way, and all the results that you saw here are in the notebooks with the sample data set on the GitHub page. So basically everything you saw here today is reproducible, and you should hopefully get the same results that you saw here.
And finally, we would like to thank our mentors, Claudia, Julia and Stefan, for the great feedback from the software development side and from the hydrology point of view on our problem, and Esperanza for communicating our results. Of course, our university and the department for providing us with computer resources and an office. And ECMWF Copernicus, of course, for setting up the challenge and providing this great opportunity. Thank you.
Okay, are there any questions? Thank you, Lukas and Sebastian.
More comment than a question. So, using dropout techniques, so you could, in principle, make the same prediction a couple of times and get different forecasts, right? Because you basically double forecast such. So it would be interesting to kind of compare the spread that you get from the zoning against the error that you're expecting, or that you're going to.
Yes, there are 2 points in that. I think one is the variability in the model. So if you run it again, later you get some hopefully similar results. So in a more detailed case study and more detailed study, you would need to determine the performance not only in a mean performance value, but also a percentile in which the model performance lies, because the model performance is not stable, of course. Sometimes it would be higher, sometimes it would be lower. But so that's the randomness that is given by the randomness in the fitting or in the prediction procedure. And what I would call ensemble is that I use different input information. So for different ensemble members of the IFS, of course, we would get also different results, which would have probably a larger spread, of course, than just from the dropout that you mentioned. Is that?
Yeah, thanks.
Yeah.
Yeah. Also for the other models, you can we set the seed. We specified the seed which random numbers are drawn so that we have a reproducible result. But you can tune that as well for some of the other models to get the kind of a randomness for every run, every forecast.
Okay, is there another question? Tommy?
Thanks so much, guys. That's really cool. There's so many ideas that you would love to kind of implement as well. So really, really good work. This might be kind of jumping the gun a bit. But do you have any sense of like the generalization capability? Run it once over a station or something, just how it performed, or whether it was similar or.
We did once. like not intended, because we took a wrong grid point, and it is a couple of 100 kilometers away, and it produced similar results, but of course a little bit worse. But I can't put a number on it.
Yeah. Just to add context, we intended to predict the other point, but it was with the trained model from the other area. So the error in there was that you have those 100, 200 kilometers of additional data points that didn't go into training, into the training for the model to predict this certain point. That was the error. But yeah, the results looked not that bad. But it was obviously, when it's 100-200 kilometers, it was at the same point at the Danube. So the upper catchment was obviously the same. But yeah, this is definitely one interesting point where future work could be based on to try it in other catchments, obviously. Well, and especially to compare it to the EA LSTM, the results, this would be very interesting.
Okay, is there any last question? Yes?
It's more a comment as well. For the Copernicus first two, and as you know, maybe in this room in about a month and a half, we will have a big workshop on artificial intelligence and machine learning applied to the whole spectrum of Copernicus. I'd like very much to have you either participate or submit an abstract or poster to this event, because I think the result deserves some well done.
Thank you.